Hey boys and girls, welcome to Munro Live. We welcome you back, and we're here at Mcity, U of M's test facility, where they're trying to produce level 4 and hopefully level 5 vehicles that will hopefully soon be driving around in. What I'm going to do is I'm going to introduce our guests here. Actually, I'm going to introduce Dr. Liu, and he's going to tell you a little bit about his background. Then we'll continue on, and everybody else that's standing here will get the chance to talk a little bit about what they do and where they actually work. So, Dr. Liu, please.
All right.
Please start.
Thank you, Sandy. My name is Munro Liu. I'm the director for Mcity. I'm also a professor in the Civil and Environmental Engineering Department at the University of Michigan. At the same time, I direct the Center for Connected Automated Transportation, which is the US DOT University Transportation Center. Besides me, this is Greg McGuire, who is the managing director for Mcity, and then two of us will be hosting you for the tour.
Well, thank you. Did you want to give a little background on?
I certainly can. I'm Greg McGuire. I'm actually born and raised here in Ann Arbor, where we're standing. Got my start in transportation in car sharing through a car sharing company called Zipcar. Did a lot of engineering for them in the early days and got bit by the transportation bug. So when I moved back here a few years ago, I had the opportunity to sign on to Mcity. It's a really interesting intersection of research, industry, government. I think it's doing kind of unique things in the world, to be honest, and it'll be fun to show it to you today.
I've been with Munro since earlier this year, worked with a partner consulting company for a couple of years before that, and my background is in electrical electronics, mostly automotive, had a couple of career deviations, but it's a fascinating field, and I'm really interested to see what the folks at Mcity can show us.
So first of all, Mcity. Mcity is a public-private partnership, and we work with industry. We will also work with academia and government, and we bring researchers together from a range of disciplines, and then we help them to address some of the pre-competitive issues related with connected automated vehicles. And as you can see from the slides that we work with industry, academia, and government. We do testing and deployment of the technology. We conduct research and do the data collection. And then we also have education mission and outreach responsibilities at Mcity. 6 years ago, that from business intelligence, and at the time that a number of companies announced that they will have mass production of automated vehicles, and in that news it shows 10 million self-driving cars will be on the road by 2020, and obviously with 2022 we don't have any self-driving cars commercially available. And so why is that? And so the reason for that is mostly because of the gap which exists in safety performance with automated vehicles. So if you compare human drivers versus computerized drivers for automated vehicles, human drivers in terms of accident rate is about 500,000 to 1,000,000 miles. So per mile is 10 to the -6 in terms of accident probability occurring, accident occurring. And if you look at computer drivers or automated vehicles or automated driving systems, and one disengagement every roughly around about 10,000 miles. And this is from year 2020 disengagement report from California. The challenge here is because there's two major challenges. The first challenge, I call it curse of dimensionality. It's a little technical, but basically what we are saying is the driving environment is very complex. And this is multiplying different category of factors. For example, different weather conditions, different road infrastructures. On the road, we have different road users, vehicles, you have truck, there's buses and the pedestrians, bicyclists, and each road users, they have different behavior. Their maneuver could be different, even in the same situation. And so the good news is that in the past 6-7 years or so, we have this deep learning models has been developed. They can handle a lot of these complex situations. And that's why 6 years ago, 7 years ago, people were bullish at the time that we might solve the problem already with these deep learning models. And they can handle these complex driving situations. And we might be able to, to have these automated vehicles massively produced in a few years because the technology is there already. So that was then why people were so bullish at the time, say, we might be able to have automated vehicle on the road in a few years. Well, with time goes on, people find that's actually
you have to go back.
Yeah.
I have a story.
Yeah.
Click back to that one
Yeah.
slide.
Yeah.
Okay, so I don't know where this one is, but I know where one is that I took a picture of, and it's in Oxford, England.
Yeah.
And it doesn't look as cool as that.
Yeah.
With the traffic and whatnot.
Yeah.
Nobody goes near it, and I didn't either. When I saw this in the middle of like a gigantic double, triple roundabout,
Yep.
I just basically rolled over somebody's grass front lawn, turned around and got the hell out. There had to be a better way, but I did see, I have a slide not just like that one. Now it's got more lights on it than mine, but I did see that before, and I'm wondering, what was that clown thinking? Yeah, who invented that? Yeah.
Well, one of the things I do want to mention, just to add to what you said, is that within Mcity, you will see different type of traffic signals.
Yeah.
There's the signals horizontally aligned. There's vertically. There's on the mast,
Yeah.
or on the wire. So there's different type of traffic signals, and the automated vehicle has to be able to recognize every one of those.
Yeah, yeah.
And so these are the complexity, the driving environment we are experiencing, and human brain, we can handle it in it's in the
Not that one.
second. Not this one, but in most of the cases.
Yeah.
But automated vehicle to learn all of that, it's not that easy.
Learning it is one thing. Latency is the big thing for me right now. I gave a speech at a company that makes flash drives, or sorry, not flash drives, but flash memory. And I went in there and they said, at the end, tell us what you think that the market needs. And I said, in essence, your flash memory has to interface with something else. And you told me in a speech earlier that you're looking at a couple of milliseconds, okay, or something like that. And I said, but when you add this all up, and I gave the example of what happens inside the Tesla, I said, I'm looking at a red light, and there's a green light on my screen. Or sorry, there's both red lights. Then this one turns green, then that one turns green. I said, that is what, if I'm going 85 miles an hour, that difference is the difference between life and death. When you need to go and look at chip on chip and stuff like that, the whole audience stood up and started applauding. It was exactly what they wanted to hear because that's exactly the direction that they're taking. So recognizing what the hell's going on with that is I don't know who can do it, but I sure couldn't. And so I got out. If a computer can figure that out, I'm sure it's going to take seconds to figure it out. And if it takes seconds,
it's too late. It's
way too late.
It's too late. Yep.
Yeah.
You also brushed on something we were speaking of earlier before the filming began, where there have been incidents of automated cars, even at level 2, seeing a stop sign, for example, on a billboard or on the side of a bus, part of an advertisement, and recognizing it as a stop sign. Because traffic sign recognition, and that's, human brain just filters that out. Says, no, it's
right.
And we'll get into a little bit of that later. We fund research in cybersecurity, so it's not always accidental. What if it's malicious? These are important questions to answer.
Well, this is where AI is going to come in as well. we can talk about chips and all the other stuff that's going on, but artificial intelligence should help us a lot, especially with this edge. I don't want to get ahead. Go ahead.
Yeah, but that's actually lead to my next slide really well. Is that although 6 years ago we have these deep learning models and trying to be able to handle these complex driving situations, over the years we find out there's another technical challenge to automated vehicle, which I call it curse of rarity. What is curse of rarity here is that because of these low frequency of long tail safety critical event, and just as you mentioned, so if you look at in terms of that stop sign on a billboard, it doesn't happen that often at all. And there's very few instances. And then if you look at automated vehicles in terms of their deep learning models, when they're trying to learn, they see very few of these cases. They can't learn from just one instance, because these learning models are statistical models. They have to have a number of these cases so that they can figure out the pattern inherent within these, right? So with these low frequency, very few cases for these safety critical event, and that's bring the challenge to automated vehicle. And so that's why you see what I will show you here is that on the left, I show you this is the probability of accident occurring. And then this curve shows in terms of where, in terms of what type of situation. So a normal driving situation occur a lot, right? And accident, we know for human drivers, it's a million miles per accident. And so it's about lower than 10⁻⁶. And in the middle is somewhere this so-called safety critical near misses. And if you look at it in terms of the state-of-art AVA is roughly around because it's 1 disengagement every 10,000 miles. So that's the gap between the current performance for automated vehicle versus human drivers. And so that's why we don't see these automated vehicles. And on the other hand, with the low frequency, the low probability, occurring probability for these safety critical event, the amount of data you need to collect to study this type of thing, it's exponentially increased. Right. And so that's why you need a lot more data for these type of situations, comparing for these normal driving situations. And so that's the difficulty these type of for this type of system, and that's why I call this curse of rarity. Is we don't have a lot of automated vehicles, but at the same time, in order for automated vehicle work, we have to collect lots of data, lots more data, even to be able to get enough number of cases to help the automated vehicle to learn from that. And so if I this is actually a video from Waymo. If I want, I don't know whether I can show that video. Can I? Oh yeah, okay. So you can see this is actually an intersection case, and you have emergency vehicle crossing the intersection, and on this automated vehicle, on the path of automated vehicle, you see actually green light, and then but we know it's for human drivers. We know it's the emergency vehicle is coming. Although I'm being given green light, I have to really stop, give the right of way to the emergency vehicle. But this is very complex for automated vehicle. First of all, they have to recognize all these traffic lights. They also have to correctly identify that's an emergency vehicle, and then given that situation, they have to find a way to stop and to give the right of way to these automated vehicles. So these cases, they don't see very often. And then with low frequency of these cases, and it's very difficult to handle for these automated vehicles.
Yes, but you know what? This is where government has to step up to the plate, because this would be a much simpler scenario if there were cameras on the corners.
Exactly.
And feeding the information to the cars that are there. And this is where I don't see how we're going to be able to ever make everything work out unless driving lanes are actually driving lanes, not all of a sudden somebody decides to paint something this way or that way. I've already had that situation happen on the first trip that I had with a Tesla. I don't understand why. I mean, if you're in the middle of a city, I want to look down those roads. I want to know what's coming at me or going at me. Cities are going to have to come up or step up to the plate to make sure that the driver is as informed as, or sorry, let me rephrase that. So the machine, whether it's a car or a bus or a truck or whatever, knows what's going on around it. And I don't see an awful lot of proposals sitting out there from city councils to say, oh yeah, we're going to do that. Because they look at it as, well, a car should just do it by itself. It does now, and all that does is add levels of complexity that we can't possibly make work. So this
Sandy,
is where,
that's excellent to my next slide.
Oh, very good.
Exactly.
Okay.
So these two challenges, curse of dimensionality and curse of rarity, and it's actually curse of rarity is on top of curves of dimensionality, because these very few cases occurs in a very complex driving environment. And so there are 3 technology roadmaps to overcome these challenges to automated vehicle. And I summarize into these 3 pictures. One is Tesla's approach. Basically rely upon cameras and all around the vehicle. And they map out in terms of the driving environment. And they train the deep learning models and to study all of that. And one of the advantages Tesla has is they have so many vehicles on the road already. So they can collect a whole lot of data to help them to train these automated vehicles.
Yeah.
However, I don't think they are there yet for the higher level automated vehicle yet. They are still at the driving assistance stage. And there's also Waymo's approach. Waymo's approach has a lot more sensors, different type of sensors. They have central LiDAR, they have LiDARs on the side, they have radar as well, and they have cameras. And they're hoping to achieve level 4 automated driving system directly, not in a step-by-step from the driver assistant develop into automated driving, and they're hoping to develop an automated driving system directly. And we know that, again, we don't have any commercial available vehicles for this yet. And the third is exactly, Sandy, what you mentioned, is that can we help these automated vehicles from the road infrastructure? Yeah. And if we can install some of the sensors at these complex intersections or complex traffic facilities, and then if we can get the information in advance, and then we broadcast this information, and so that automated vehicle will receive this information beforehand. They don't have to recognize what will be the color of traffic light. They don't have to recognize whether this is a emergency vehicle. The roadside know a lot better, right? So because you have a fixed camera, you can fix location to put your sensors, and you can detect all of that. And you don't have the line of sight issues, or at least less line of sight issues. And so if you have additional information, can help automated vehicles to avoid these corner cases, low frequency safety critical events, then this might help to deploy or to accelerate the deployment for automated vehicles. So I think what we do at Mcity, in summary, in terms of the research project for us, is we're not really developing automated vehicles. We're developing the technology to test and evaluate automated vehicles. At the same time, we're developing technology to help automated vehicles. So looking at basically from the environment perspective to help automated vehicles and to deploy these quicker.
I like how you say automated vehicles, because the phrase autonomous vehicles is out there too, and I think you're correctly saying automated. Yeah. And I guess I'm asking you, is the jump from automated to autonomous that 2 order of magnitude gap that needs the artificial intelligence, the machine learning, the neural networks, and And that's that huge gap that's so hard to get to.
Absolutely. The autonomous usually refer to sort of driverless, right? So the sort of driverless. And when you say driverless, particularly if you compare that with a human driver, and that's the gap we have. And then if we want to deploy these automated vehicles in a massive manner or commercially available to regular consumers, you have to overcome that gap. And probably even better than in terms of safety performance for human drivers.
Yeah. Well, I tell you, I've read a lot about what happened when cars first came into the marketplace. And the traffic light was invented but resisted because, after all, you don't have to have that with a horse. And it took quite a bit of crashes and stuff like that before even stop signs. They didn't need them with a horse, right? The horse wasn't going to bump into another horse. It just didn't happen that way. So I believe that it's going to see that, if you want to talk about a one long tail, that's what's going to be the problem, is city councils trying to determine whether or not they're going to help the situation or try and slow it down. And that's all going to be back to how much does it cost?
Yeah, Sandy, I think, you talk about some of the unintended consequences of the automobile. And we're talking about technology here today, but there's a whole social sciences aspect here that's at least as important, and probably with maybe less clear outcomes even than the engineering, that can't be forgotten and missed. That's the other half of what Mcity does, and the kind of research that we fund in law, sociology, psychology, all the things that we were talking about on the shuttle ride here. How will human behavior change? How do we prevent some of the uses of this technology that will ultimately make our quality of life worse? The technology doesn't care one way or the other. It's how we apply it.
Well, I have an expression that I work with people. If they're coming up with something that's radically different, radically new, I tell them that it's going to be 10% technology and 90% psychology. And quite frankly, when I went to school, I took zero, no psychology, no philosophy. I didn't want to even learn new words. I skipped English and stuff like that. I only wanted to be technical because I thought that if I had math and science, I'd win every day. But in actuality, when I started my own business and people started calling me names or trying to pick fights, when you're trying to get people to change, it's a big, big deal, a huge deal. And so I used to trade time with Stanford. I would get a chance to talk to their psychiatrists, and I gave a class on how we design products for lean design, our lean design method. And I think the same thing is going to be true here. There's going to be Luddites that are going to hold us back, and that's a fact. It just happens. People get stuck in the old ways and they don't want to move or change. So the psychology of changing everybody's mind is going to be a really big deal, huge deal.
All right, Sandy, let me explain to you first, and then we can do the test runs for us.
Sure.
So first of all, I want to say that we are not developing automated driving systems. We are testing automated driving systems. And right now, the vehicle is equipped with what we call what they call AutoWare, which is an open source automated driving system. It's because it's open source, it's not really working that well, and sometimes you feel a little bumpy, but that's their automated driving systems, and we're trying to develop a set of methodology to test the performance of automated driving systems. The key to test any of these automated driving systems is to provide the automated driving system with a naturalistic driving environment, right? So you want to put automated vehicles in a naturalistic driving environment. And as I explained to you, that this is in Mcity, this is an empty freeway, and in order to provide that naturalistic driving environment, we use simulation. And so on your screen, you see on the left is the simulation models. This is an open source simulation model as well, and this is called Sumo. And then in that simulation model, that's a replica essentially of Mcity test track. And on the right hand side of your screen, you see that automated vehicles there, and that's the RUS operating system. And they basically visualize where the automated vehicle is, and then where the other vehicle, surrounding vehicle is. Right now, we have not started yet. You don't see anything over there, but that's that's the beginning. So as I mentioned, the key is to provide a naturalistic driving environment, and we use simulation to generate that naturalistic driving environment. And in addition to the physical infrastructure Mcity provide to this test vehicle. And so the key for us is to control all of these virtual vehicles within the simulation model and to run, and then to see in different type of situations how this automated vehicle will react to. And so we will run two scenarios. One is what we call naturalistic driving environment testing. And what it is that it's just like a nature in public road. You're driving on public road. You have some vehicle surrounding you, and this automated vehicle you drive normally to it, and doesn't it will see how this vehicle react to it. The second run to that is that for us to test automated vehicles, if we just let automated vehicle run on naturalistic driving environment, it will take super long, because in most of the cases in a naturalistic driving environment, nothing really happens. It's all normal driving situation, and there's no challenging scenarios. And so it takes a very long time and to test automated vehicle performance. And some of the report shows it takes billions of miles to validate the performance, the safety performance for automated vehicles. So to test automated vehicle, we have to accelerate this process. And in order to accelerate the process, we have to generate these adversarial scenarios and the challenging scenarios to automated vehicle, and so that the automated vehicle see more of these challenging scenarios, and then we can test their safety performance. So we will do two test runs. One is what we call naturalistic driving environment testing. Another one is naturalistic and adversarial driving environment. So most of the surrounding vehicles, they are naturalistic, but some of these vehicles, when they see opportunity, they will challenge automated vehicle. For example, they might cut in, they might do some abrupt lane change and things like that to challenge automated vehicle and see how automated vehicle react to it. And so that's how we accelerate the testing of these automated vehicles. Right now, we only test this in a stretch of freeway, but we can expand it to the whole Mcity with urban situations as well. Right now, you can see that simulation is running, and then the AutoWare is running too, and you can see some of the virtual vehicles. Let me just get started. So this AutoWare will take over, and then I'm hand off right now. And so this automated vehicle is driving, the automated driving system is driving the vehicle. And then you can see that this actually have surrounding virtual vehicles, right? So these are virtual vehicles fit to automated vehicle. And then right now we are in a naturalistic driving environment. Most of the cases are normal driving situation, and so the vehicle doesn't really feel anything different. And so this is just like driving on a public road.
So I noticed that there's a pretty dramatic amount of. Oh, I see. There's a car in front of you right now. Okay.
Yeah.
Yeah. You have to wait for that, I guess.
Yeah.
Yeah, okay.
Okay. Yeah.
So why is the brake hitting so quickly there?
Yeah,
what is
this is the auto-wear system. So sometimes they, just the control system of auto-wear is not really developed that well. So sometimes they, the algorithm itself is have some abrupt deceleration.
I see.
So it's not our, we developed a testing algorithm, and we rely upon the auto-wear to control the vehicle.
So it didn't see the traffic light you just went through?
Yeah, it didn't see. It has all the driving. You can see it has all the virtual vehicles running, but it's in the it's naturalistic driving, so it doesn't have any challenging environment. But so this is, you can see that when they do the curve, the control system didn't doing very well, and they have some abrupt.
I thought it might have something. I noticed you're going about 20 miles an hour. I thought maybe it has something to do with if the acceleration goes a little too far, it wants to cut it back, like right now.
No, not really. It's mostly because they are, it's on a curve, and their control system is not really designed that well. So sometimes they have some, discrete deceleration. So the second round we're going to do is we're going through this naturalistic and serial driving environment. So it will, the surrounding vehicles, when they see opportunity, and the computer algorithm, when they see the opportunity, they will challenge automated vehicles. So they may cut in abruptly, and then the vehicle has to stop. So you may experience a little bumpy ride there.
Yeah, I see.
Maybe we can accelerate a little bit and then start. Yeah, we can start.
So you can see that there's this is the actually the
We got hit from behind.
you can see from this vehicle actually is being hit, but from the behind.
Yeah.
Okay, you want
Start the simulation. Just getting a virtual car crash.
the virtual car crash, exactly.
I had virtual neck
Okay.
brace. Oh.
Let's start.
Yep. Oh, we can accelerate a little bit and start.
Okay.
So it might be a cut-in, might be.
Yeah, that might be a cut in from the red lane. The vehicle is in the red lane. Okay, you can see there's a cut in, and then there's a crash over there too. So
We just had a crash?
yeah, we'll have another crash, and the vehicle from the right lane actually in front of this vehicle and the red lane, they merge into this lane, and then so that's why we had the crash.
And start. Oh,
Yeah, it did.
And there's
yeah.
another
Yeah.
vehicle in.
it's really.
Man
Yeah.
alive. This is just a very realistic of driving in Michigan. Yeah. Yeah.
So that's the two round, and basically what we're trying to do here
Wait a
is
minute,
to
we're on the
develop this.
infield here.
Yeah,
That-
no, I take it over.
Oh,
now.
oh, you
so
take it
I
over.
take it
Oh, I
over.
see.
So
Okay.
so we're right. What we're trying to do is trying to develop this driving school essentially
Yeah.
for automated vehicles, and then to to basically to test them in different type of situations. Particularly, we want to accelerate the testing for automated vehicles so that we can train them faster, we can test them faster, and that's although we only showed you that just a small demo for the freeway situation, but it can apply to the whole urban situation as well. And so that's why we call this is a mock on-road test. So because this is essentially a simulated test track test, but we're trying to simulate on-road naturalistic driving situation.
So I would say, this vehicle is approaching the automation problem from the top end down, so it's, you know, very safe, but it's very cautious as a result. And its, you know, capabilities are much more limited. It runs in on a virtual rail through time and space, but it always repeats the same path over and over. It doesn't deviate. So this is an early generation of an automated system, and I think some companies are coming at it from the other direction. You know, start with a functional service or a functional vehicle, and add automation as you go up the stack.
One thing I've seen with campus type vehicles like this that are geofenced, well, very similar to this shuttle we're in, is the residents or the workers or whomever on that campus mess with the vehicle by faking to step in front of it, pretend they're going to move, and then the vehicle does this stop start.
Yeah, like it's doing.
They're kind of messing with their colleagues in doing so, and I'm not suggesting that, you know, this is pedestrian access friendly here, but
I think the human behavior element and how automation mixes with human behavior is one of the most interesting pieces of the whole race to autonomy. And that kind of example is an extremely good one. So we're here in the University of Michigan's Transportation Research Institute's high bay, where the magic happens. Remember I said Mcity is a public-private partnership between government, industry, and academia. This is the academia. This is Jim Sayer. He's the director of UMTRI, of our Transportation Research Institute, and he does. This is where, you know, the actual research happens.
So we actually consider ourselves a boundary organization. We're somewhere between the pure academics and industry. We're all sponsored research. So we don't bring in research, we don't get paid. It's that simple. That's how we keep the doors open.
He's got research or die tattooed on his arm.
Yes, or die, or at least don't get paid. So we oversee like a lot of large field operational tests. We oversaw the deployment of connected vehicle technology in roughly 3,000 vehicles here in the city of Ann Arbor. And all the data associated with that, which we then share with other academics so that they can mine it and use it to answer research questions that they have. We've got about 20 research faculty and then about 60 full-time staff, engineers, sociologists, statisticians, just a very multidisciplinary institute. This vehicle over here kind of looks like a little bit like a Frankenstein, but it's this way intentionally. We're doing some work looking at what are the optimal types of sensors and the optimal placement for various types of crash scenarios. So this is really just a mule platform for us, but allows us to swap sensors in and out and examine kind of the performance of the different sensor types in different types of crash scenarios.
I see. So is that LiDAR at the top, and then I see cameras, and I also see, is that radar?
These are radars, These are short range on the side. These are 27 gigahertz. 27, 28 gigahertz, I don't quite remember.
1 gigahertz among friends, is okay. Yeah. So what do we got here?
What we got here is we have a prototype wheelchair anchoring system. So we do testing, crash testing with wheelchairs. And if you want to climb up in here with me. So one of the things, sure, So one of the things that people who are confined to wheelchairs comment about a lot, particularly in the day and age of COVID, is their ability themselves to get into a vehicle, a transit vehicle, without having to rely on, you know, the driver, for example. This is a system that's been developed here, which is a universal docking system. And it is intended by if you add a couple of bars here, the wheelchair, some wheelchair users, not all, depending on the level of their disability, would be able to back up. And once backed up, once engaged, the system
Docks.
out, right, spreads out and holds onto these bars. Similarly, there's a rod that comes down which is carrying the seat belt, and it locks here in the floor. So it turns out that this is actually a lot more quick than having to use a traditional tie downs
Yeah.
and having to anchor, and there's less error in terms of properly anchoring the wheelchair.
Well, I've always wondered why they don't have a docking station for wheelchairs. I've seen this any number of times, and it really doesn't fill me with confidence. These are people that definitely should be taken care of, and I think that this looks very interesting. I'm not exactly sure I know everything of how it works, but I can see down there that attachment place for the docking.
Yeah.
And,
So
so you'd add one feature to the wheelchair. It
yeah,
looks like?
yep. You add these rods in the back,
Yeah,
and then once the wheelchair user has backed up against this, they push a button, and it causes those clamps to come out,
Right.
spread to hold the wheelchair in place. And you press a separate button, and then the seatbelt bar comes down and locks in the floor.
Very good. So this is like not a guillotine, but a swinging arm, then, right?
Yep.
So the swing arm comes down here and locates in there. So
Correct.
Eric, if you can swing up and catch the other end of that bar, it's right there in front of you. That big thing. Yeah. So yeah, I've never seen anything quite like that. So this is a new one for me. And we have worked on loading devices for wheelchairs, but never the locking device. Everybody has something similar to that. It's kind of in the marketplace now, and you know, it's kind of an afterthought to me. This looks like an invention.
There are other systems that clamp the wheelchair
Yeah.
by grasping the wheels, though those normally wheelchair occupants have to ride backwards
Yeah.
in order for those to
Yeah.
work. But then you have the problem of motion sickness, whereas
Right.
this system allows people to face forward.
So what is a sled test like? How many miles? Or
This is a equivalent of a 30-mile-an-hour crash.
Yeah.
This is called a rebound sled. And right now that chair is strapped in for a test tomorrow morning. This is some work we're doing for the U.S. Department of Transportation. But yeah, so with all the really super bright lights and high-speed cameras, you can film in excruciating detail where there are failures, and of course then they have landmarks on the chair and on the crash test dummy.
Yeah. Yeah. So do you have sensors for load on all this?
Yeah. Yeah, so they'll be measuring the load. They'll actually look at the deformation of the chair after the fact. And obviously accelerometers in the test dummy. And they'll be looking at how far forward the dummy projects at impact.
Oh, very good. Okay, well, thanks for tuning in to Munro Live. We're standing here in front of the sled test that I'm very, very interested in, because I believe that this is an admirable thing to work on. I'd like to thank all the people here at U of M. I'd like to basically say that this was really worthwhile. I hope you enjoy it. And on behalf of the three of us, I'd like to say thanks again for watching Munro Live. Stay tuned for more stuff. Thank you. Bye-bye.